Okay, so last class we talked about uh, various methods, sort of variants of gradient descent, incorporating things like preconditioning, momentum, adaptivity, and all the other tricks in the book, right? And then we switched topics and started talking about online learning. And within that, we started talking about mistake-bounded model. Okay. Today, what I'll do is, we'll look at why perceptron works when you have margin. And then, maybe briefly talk about the connections between online learning and optimization. And then we'll switch to a topic which is much more widely used, that is regret minimization, and one of the very important algorithms called multiplicative weights update method. Okay, so these are the things that you want to do. And just as a reminder, assignment 1 has been posted online. Okay, and it's due April 21st at 10 p.m. So if you haven't been able to access it, you should be able to access it through Gradescope. If you go to Brewing Learn, just register for it on, just join the Gradescope for the class, and you should see it there. Okay. All right. So we were oof, we were talking about the perceptron algorithm. So let's go to that. Okay, so this was the perceptron algorithm, and we just said, it's a very simple algorithm where you get a vector, and with the current candidate classifier, you try to classify it, and if you make a mistake, you correct yourself based on the direction suggested by the exam. Okay. All right. So what's the guarantee that we know about this? And we also define this important notion of margin. And very nice fact is that perceptron actually solves the online learning problem when you have margin. So perceptron makes at most 1 over gamma squared plus 1 mistakes. Okay. And the proof of this is the following. So first, observe that when we don't make a mistake, the algorithm does nothing, right? And typically in these scenarios, what you want to do is to kind of build some kind of potential function and say that when you make a mistake, something nice happens. Okay, so that's what we're going to track. And intuitively, what we'll track is to say when we make a mistake, somehow we improve our current classifier by making it sort of point more towards the true unknown classifier. Okay, so we make some progress towards the unknown one whenever we make a mistake. So okay, and one way to measure progress towards the classifier is to say the following. So we're going to measure the correlation with the unknown W star and argue that whenever you make a mistake, your correlation with it increases a little. So you're going more and more towards the true unknown W star. And that kind of conforms with our intuition, right? That's how we design the algorithm. If you label some point wrong, then you should try and move towards W star. That's what our intuition was. And that's exactly what the calculation is going to show. So let's calculate how the correlation with the unknown W star changes. Okay. So you take this inner product, and then you have this Wi minus 1 times W star plus yi times xi W star. And so what do you think this quantity is? So yi times the inner product between the example and W star. Can it be positive, negative? What do you think? Well, remember, the way the data is being generated was you had x, y, and our belief was that y is actually this sign, right? So, so what can you say about this inner product, this product? It's non-negative, and it's in fact always just the absolute value. Right? So whenever this inner product is negative, excuse me. Okay. yi is -1, so you get the absolute value always. Okay? You're just picking out this sign, right? And what can you tell me about this number? We want to say that the correlation is increasing. So at least qualitatively it is increasing because the correlation as measured by this dot product is, you're adding something which is positive. Okay. But can we say that we make some noticeable progress, that you're not just adding something non-negative, you're actually adding something which is noticeable? What about this number? Can we say anything about it? Yeah. Exactly, right? So that's where margin comes in. When you have margin, the point is it helps you in saying whenever you make a mistake, you actually make some noticeable progress towards the unknown W star. Okay? So you get okay. So what we learn is that every time you make a mistake, our sort of the potential that we're going to track is this inner product, and that is going to grow. Okay, which sounds very good. You're always increasing the correlation, but there's one catch. Can you imagine why this is by itself not enough? The reason is that, somehow, okay, you are increasing the correlation, but also you're increasing the length of your classified WI, right? I could quote unquote increase my correlation by just multiplying it with like a factor 2. But that's not real progress. So somehow you have to balance the two because I'm adding a new vector, right? I'm adding something here. So I might be increasing this length a lot more than the progress that I actually showed in the correlation. Okay, so you have to balance these two things. And as it turns out, actually, that is what we can show. Okay. So to counterbalance that, the fact that we're increasing the norm itself, we can control it. Okay, so we're going to show that the length will increase, but not by too much. It's not like you're increasing by factor 2 or something. It never increases by much more than kind of the case where they're perpendicular. Okay. Why is this true? We can draw a picture. So I'm really going to draw sort of this picture. Okay. So we made a mistake. Again, all of this is happening in a round where we made a mistake, right? So this is Wi minus 1, and this is yi times xi. And this is a new vector wi. Okay, so I have my previous classifier. I updated it, and this is the updated classifier, right? And the point that we're going to actually show is kind of depicted in this picture is this triangle is always going to look like this, that this angle is going to be obtuse. Okay, so that's what we need, right? And yeah. So the key point that we're going to show is that this angle is always obtuse. Okay, so let's try and show that. So again, we have exactly the formula for the update. So we can calculate the norm squared, which is the inner product of the vector with itself. Okay. And if I use the inner product formula, I get okay. And here I'm using the sort of extension of Pythagoras' theorem, which says that when I add two vectors, the length of the resulting sum is just sum of the lengths plus 2 times the inner product between them. Okay, this is like the cosine formula for computing the length of the third side of a triangle given the angle between them. Okay. So I'm just applying that with this as u and this as v. Okay. And so this is wi minus 1 squared plus norm of xi squared plus 2 times yi and x, right? And we know this is just 1 because we normalized everything so that all of our points are on the unit sphere. And what about the second term? Is it positive, negative? Is it always going to be in one direction? What do you think? And if it's in one way, why? Go ahead. But why is actually I should have said it's always acute, I think. Yes, you're right. This angle is always acute. Okay, so why is that? So why is this acute or right? Right, but why is this always negative? Exactly, right? So we are only making the update when we make a mistake. So that's important in this calculation, right? If you actually made an update every time, then we wouldn't be able to make this sort of control, right? So you should only update when you make a mistake, okay? So, I mean, it's kind of meaningful to say you learn the most from your mistakes, but here we're saying something even stronger. They should only learn when you make mistakes, okay? So why is this always negative? Well, we made a mistake. Means yi was not actually the sign of wi minus 1. What our previous classifier predicted was the opposite of yi. and this is 1 or minus 1. So the product will be negative. Okay. So that means this is at most Wi minus 1 squared plus 1, just because this is negative. Okay. So now we're in good shape. We're saying that the correlation increases, but at the same time, the correlation is not just increasing because we're scaling up the vectors. The length is also growing, but not at a faster, very fast rate. Okay. So we can now put the two things together and say, suppose we've played the game for n days. We have been keep playing the game. Every day we get an example, we make a prediction. If you make a mistake, we get some penalty, right? So we played the game, for however many days, and at the end we made capital M mistakes. Okay. So what does this mean? So in this case, by claim 1, we know that Wn comma W star is at least gamma times M, right? Because every time we make a mistake, we increase gamma, right? So every time we make a mistake, we increase it a little bit. So it's at least M times gamma. Okay. And how about the other direction? We also know that the norm of Wn squared is at most M, right? Because every time we make a mistake, we increase the norm squared by at most 1, right? So, maybe this should be 1 because we're starting out with something. Okay. All right. So now we just have to balance the two, and so we have gamma M is at most Wn comma W star. Okay. But if I use Cauchy-Schwarz, the inner product between any two vectors is at most the product of the lengths of the vector. Okay. So this is at most for any two vectors, the inner product between them is at most the product of the lengths. Okay, so that's what we are using. So we get this sort of weird looking identity that gamma times M is at most square root of 1 plus M. Because, we have this bound, and this is always 1. Okay, and, you can solve this quadratic. And if you solve this quadratic, you'll just get M is at most 1 over gamma. Okay, so you just have to solve for this quadratic, square it, give the solution, and you get 1 over gamma. Okay. Any questions about this argument? So two things here. One, we are saying that the correlation increases, but it's not just because the length sort of blowing up. There's something more nice happening. Okay. All right, so very simple algorithm, very simple analysis. But as I said, at some point, this got hyped up to nth degree. You can read up the history. It's a very fun sort of anecdote. Okay, but I'm not going to do that. So one thing that I do want to mention is that this perceptron is actually, as an online algorithm. So let's recall what the algorithm was. Okay, so this is the algorithm. And you can actually initialize, sort of set up a ERM problem with an appropriate hypothesis class, parameterized hypothesis class, and a loss function, such that if I just use stochastic gradient descent on this loss function, you get back this exact algorithm. Okay, so this is one of the nice features of stochastic gradient descent, which is that it is an online algorithm. Okay? So what do I mean by that? You can imagine running the thing where every time you get a sample point xi, yi, I can compute the gradient of like the local gradient at that point and update my current set of parameters. And then forget about what is in the past. Except for the current set of parameters, I can keep forgetting what is in the past, right? So in that sense, SGD is an online algorithm. So let's just, sort of maybe see it in action. So I'm going to define oh, okay, I see. Okay. So let me define a hypothesis class, which is just, what we are looking at. Right? It's some discontinuous function, so you'll have to use you'll have to use subgradients, but that's okay. We don't have to worry about that too much, right? But the loss function that we're going to use is the following, is hinge loss, right? And what is hinge loss? Hinge loss just checks, so imagine we're just comparing like, these are 1 or 1 and 1 or minus 1 value. And the loss should be 0 if both of them are the same sign, right? If they're the opposite sign, you should get penalized. Usually in the 0, 1 loss, if they're the opposite sign, you just say, okay, loss is -1 or loss is 1. Okay, you're giving a number irrespective of how badly off from the sign you are. So for example, if the true label is 1, but my sign prediction is like 0.1, I get some penalty. If it's 0.1, I don't get any penalty. But if my prediction is like -0.1, then I get some penalty. But if I'm way more negative, then I should get more of a penalty, right? Instead of just looking at the sign, hinge loss says you should also look at how far off on the negative side are you, okay? So in particular, so imagine I plot A times B here, okay? So if both of them are on the same sign, I want the loss to be 0, right? So that's what my function is going to be like. Whenever, this A and B are both matching in sign, the loss is 0. But if they're not matching in sign, I penalize for, saying even more negative things. Okay. You were supposed to say positive, but you said -0.1, you'll get -0.1 or 0.1 penalty. You were supposed to give a positive value, but you said -100, you'll get a penalty of 100. Okay. So in fact, I think this is a more reasonable loss function, right? So you're not just penalizing for the sign, but also how far off are you? Okay. So this is hinge loss. So with these things, we can define the loss function as what would the empirical loss minimization problem be? Okay. So let's call this function phi for the hinge loss. Actually, I should not put the sign here. Okay, so this is what you get. And you can compute the sign, and then it's clear that, if when you compute the gradient, basically if the signs match, the gradient is here, so you'll be 0. There is no gradient on this side. So that means you don't make an update unless you make a mistake, which is what perceptron was doing. And when you make a mistake, it's just yi times xi. Okay, so this is a calculation that you have to do, but uh, so if you calculate the gradient, it's going to be 0 if your prediction, the sign is actually correct. Otherwise, you get exactly what you were at. Right? I think there's a minus here, sorry. So when you do the negative of the gradient, you get the right? So this is just to say that this is equivalent to SGD with linear predictors and hinge loss. Okay. And also to say that SGD is actually an online algorithm. So for many online learning problems, you can actually use SGD to solve it. Even though you cannot use full gradient descent, you can still use SGD. And some of the intuitions for AdaGrad and Adam, etc., do come from like the online learning literature. Okay. So that's all I wanted to say about perceptron and its connection to online optimization. Let me now talk about a much more powerful model / framework for online learning. Okay. The mistake bounded model, I would say, is maybe sort of the best case scenario. If you can get a mistake bounded algorithm, then you should perhaps use that. We saw how to do it in the presence of margin, but in general, you cannot hope to get mistake bounded algorithm. Okay. It's a very strong requirement, which is not usually possible. Okay. What do you do in that case? You study something, study a more relaxed goal, which is called regret minimization. Right? And this will also allow us to kind of work in a much broader setup. So we'll abstract away much of the learning and make it into like a game. And once you have this game, you can actually use it for many, many different applications. So it's this particular algorithm that I'm going to talk about has been discovered several times. It's been discovered in quantitative finance because it's used for portfolio management. It's been discovered in economics, in game theory. It's been discovered in learning theory and so on, because it just shows up in many, many different places. It's been used in optimization, classical optimization literature as well. Like 4 or 5 different communities just came up with the same algorithm. It just goes to show independently, actually, just goes to show how central this is. Okay. And to define, the problem that it's going to solve, let's me define a game. And this game is called, or it's just learning with experts. Okay. So what is this game? Okay, so the game is as follows. So when we think of learning, we usually say you have some examples and some predictions, history, and then you're trying to make a new prediction, right? In learning with experts, we're going to get rid of all of that and assume something even more crude. Okay, what is the assumption? We don't even get to see the examples exercise. Okay, you might ask, okay, if you don't even get to see xi, what are you going to make your prediction based on? Okay? So what you get to make prediction based on is you have some other surrogates, some other predictors whose prediction you know. Okay, so imagine like, basically like you're trying to do stock trading. The ideal thing you might want to do is, okay, I'm going to download all of the data in the whole wide world to get all of the past history, every news item, and then use that to build a model to make a prediction. Okay, the other maybe lazy way is, quote unquote lazy way, is to say, I'm going to just take maybe 1,000 experts, whoever they are, and they make their own predictions. And somehow I'm going to use that as my only information. And based on those predictions, I have to make a prediction. Okay. So this is learning with experts framework, meaning we just interact with the learning task only through what some experts say. So we have a bunch of experts, E1, E2, E3, and so on. Let's think of having D experts. Okay. And again, this is an online learning problem, so we play this game in rounds. Okay. So each day we what am I each day we get the information from all of the experts, whatever they're predicting for that day. Okay, so in the early morning, 9 a.m., we open our newspaper. Okay, not anymore. Even I don't do that. So, like, you open your Twitter feed and you have all of these financial experts that you're following. You're like, okay, this person is saying up, down, and so on. Maybe you'll put Jim Cramer there. Maybe you won't. Okay, but you have a bunch of these experts, they're making a prediction, right? And then based on this input, you have to make your prediction. Okay, and then you can use whatever rule you want in how to aggregate the prediction. Jim, here maybe everyone is saying up, so we'll be like, oh, okay, everyone is saying up, let's also say up. Okay, so in some sense, the example or the features that we see is just the sequence of predictors, nothing else. Okay, so it's like a d-dimensional input where the input is what these experts are predicting. We make our guess based on these predictions, and then just as in the online learning game, we are shown the true label. Okay, everyone was wrong and the market went down. Okay, so whenever you make a mistake, I'm going to describe kind of a simple model where it's just binary prediction, but it naturally extends to, like, really not just the direction, but you might also ask, okay, tell me how much amount. Okay, as long as it's, and you can put any number there. It's everything that we discuss will work, but it's much better to only think about this for the time being. Okay, so the truth is down. Bunch of people made a mistake here. Like, this person made a mistake, so the expert one got a loss of one. This expert got a loss of one. This expert got a loss of one. This expert got a loss of one. We also got a loss of one. Okay, But there was one expert who did well and got a loss of 0. Okay. And then day 2, you do the same thing. You get some predictions, down, up, down, whatever. Okay. And then based on that, we make a prediction and the market says something. And then you go back and evaluate or check, this expert got a loss of 0, this expert got a loss of 0, 0, we got a loss of 0. Okay. So this is the game, learning with experts. There's no sort of classifier or anything like that. It's just trying to follow the experts. Okay. But the online thing is that somehow you don't know a priori who is the best expert. You have to somehow infer this over time. Okay. And at the end of the day, you measure the total loss. So you have some number here, which is the loss of E1, loss of E2, and so on. Then we have, our loss. Okay. So let's just set up some notation to make it easier to talk about these things. So let's say L of t comma I is loss incurred on day t by expert I. Okay. And L of t is just loss incurred by our predictor. Okay. So now, what should the goal be? Should our goal be to have very small loss? Is that a meaningful goal to achieve? No, right? All our experts could be garbage. Then we are getting garbage in. There's no way we can refine it. Okay, because our only interaction with the entire information system is through what the experts are predicting. Okay, so we can't just say, okay, minimize the loss, because we don't know how to minimize loss, or there cannot be a meaningful solution to minimize the loss. So what would be a better goal then? Like, what's a good model or target to achieve? What's a good benchmark? Exactly, right? So I don't know how the experts are going to do, but I want to be as good as the best expert in hindsight, right? If you show me the entire thing, obviously it's very easy to go and say, okay, expert 1 did very well, so you should have followed expert 1 throughout. Okay. But what we really want to do is match the performance in hindsight. Okay. So now you can see kind of, how or why this kind of sort of modeling task shows up in quantitative finance, right? Because you might even have this expert could actually be humans or making the predictions, or they could themselves be completely different models that you built. Right? Maybe you have one research team which used, let's say decision trees. The other team used some kind of other, maybe neural networks. Something else used some automata theory or whatever, right? Or then I have just people making predictions. So thousands of different models that I've built, and you can imagine having some kind of aggregator which doesn't know which of these models is the best one, but is trying to match the best one in hindsight. Okay, so it's very applicable in sort of ensemble learning, where you have different models and you're trying to aggregate them in some way. Okay. All right. So the way to exactly define it is the following. Quantify matching the performance of the best expert is through what's called regret. Okay. So the regret at time t, or the total regret at time t, is the loss that I incur so far. Okay, over all of the first t days, I incurred some total loss, right? And I want the gap between that and the loss of the best expert to be as small as possible. Right? I want to match the performance of the best expert as closely as possible. So you look at the loss of each expert, the total loss of each expert. And this is the loss of the best expert. If this is 0, I should be very happy. So somehow I figured out or matched the performance of the best expert without even knowing who that person is going to be. Okay? You cannot typically expect 0 loss, but you can get close to it. Okay, and that's what we're going to see. Okay, any questions about the model? And as I said, it's very generic, right? So we're not assuming anything about the expert or how they are making any predictions. You can make those assumptions and get stronger guarantees in some case, but right now we're not making any assumption. They could be models, they could be very, very complicated systems. At the end of the day, we're going to say, as long as you have some D experts in some number of rounds, we will try and match the best expert with just their predictions. Okay. Yeah. You're basically saying, is there an anti-Jim Cramer sort of idea that you can use? And if you get this joke, but anyway, so if there's an expert who's consistently wrong, then you can potentially do the opposite of that expert. That's what you're asking. I mean, that's potentially possible, right? You can think of models like that, but at least it's, one way to think about this is just put that XOR as a new expert. Okay, that's the way, that's one way to do it. Just imagine I have the flip strategy where, I have E1 complement or negated E1 expert who is always going to do the opposite of E1. Okay, that's like my new expert that I've added to the mix. And then I can run the same sort of simulation again. Okay, so that's why it's very flexible, right? You can create new experts out of this. It might increase the time complexity, but then you can try and match the best expert even among these new experts. Okay, makes sense? Yeah. Like, that's a very good question. You can imagine, maybe I'll combine these 3 into something, the other 3 into something, and so on. Just put them as other experts. Okay. Sometimes you can even be more efficient, even if there are exponentially many experts. We'll talk about that later on. You can do better without even looking at what all of the experts are predicting. And that's particularly important in reinforcement learning, as we'll see. All right. So this is our goal. And let's start discussing strategies now. We have a concrete algorithmic problem now. We get these inputs from the experts, and then we have to make a prediction. Okay. All right. So what's maybe the first strategy you would think of when I say you have to figure out or match the performance of the best expert? Best so far. And that actually has a name. It's called follow the leader, or FTL, right? So you define a leader as the expert who has the least possible loss so far. And makes intuitive sense. If an expert is always making mistakes, just throw that person away or never sort of follow that person's prediction. Okay. But if an expert is consistently good, you should maybe follow that person's advice. Okay, this is follow the leader. Among all of the experts so far, in all of the rounds so far, whoever has the least loss, just follow that person. Okay. But my claim is that, this is not a particularly good strategy. So what can happen here? Exactly. So you can actually have a scenario where if you follow this, you'll end up with a regret with a factor of D, depending on the number of experts. Like in every 1,000 rounds, you'll be right once or something like that if you have 1,000 experts. Okay. And as I said, you should really think of there being many, many experts, because when I say expert, we're thinking humans, but it's not really humans. They could be different signals that you aggregated by different models or whatever else you have. So you should imagine the number of experts is thousands, 1,000 or more or something like that. Okay. All right. So what's the problem? Font is very okay. So I'll share this too. I just need to figure out where to actually host this website. But this is like the experts framework, right? You can think of the days as rounds. You play a game over rounds. Here I have 3 experts, and you just say, yeah. So each day you pick some expert to follow, they make some predictions, and then you make a decision. You say, okay, I'm going to predict one, and then you incur losses. Like, my current loss is this much, expert one's loss is this much, expert two's loss is this much, and so on. Okay. This is the game that we're playing. And now let's look at follow the leader. What happens? Okay. And each round, we identify the expert who has the least amount of losses so far, and you just follow that person. And the problem here, as was pointed out, is that basically the moment we decide to follow an expert, that's the moment that person makes a mistake. Right? Because we're not assuming anything about the consistency of the experts. We have to figure it out on our own. So for example, let's say we have 10 experts, and so far all of the experts have 0 losses. And if the experts have the same loss, you pick the first expert, whatever ordering that you have, right? And say play. So on the first day, the first expert makes a mistake. So we decide to follow expert 2. The second day, the second expert makes a mistake. And the third day, third expert makes a mistake, and so on. Okay? But the end result here is we are wrong every day, because we are choosing the expert who is we are really flip-flopping, right? We keep chasing the ghosts, as it were. Okay? And you end up being wrong every day. Okay? So if you have 1,000 experts, then you'll basically end up being wrong like 1,000 days in a row. Whereas there is an expert who is consistently correct. So the best expert has 0 loss, but we are wrong every day. So follow the leader can be a terrible strategy. Okay. All right. So we'll talk about other stuff here later on. Okay. So can have losses completely. Okay. So it's not at all a very good strategy. So to decide what else to do, let's think of a special case. which is, which showed up even in the FTL case where, let's assume that there is actually a very good expert. We don't know who that person is, but there is indeed a very good expert. In fact, I'm going to assume something very strong just to get an algorithm, and then we will refine it to work in very, very general setup. So let's assume there is an infallible expert. Meaning, so this is sort of the toy case or elementary case where I'm going to assume that suppose there is an expert. Yeah. So they can right now, all the losses are 0 or 1 valued. Okay. So in some sense, the only thing we know is, okay, this expert incurred a loss of 1. This expert was correct, so incurred a loss of 0. Okay. How the loss is measured is also can be generalized. Okay. So right now I'm saying, okay, you predict up or down, and there's some underlying ground truth, but you can ignore that too and just say each expert comes with a tag of a loss. And then you have to pick which expert to follow, and your loss is going to be whatever loss that expert incurs. Okay. And, we'll talk about the more general thing later on, but already this will give you the right algorithm. Okay. Right. Suppose there is an expert who never makes a mistake. Meaning there is an expert who is 100% correct, whose the loss is 0 all the time, right? So that means the loss of the best expert is 0. Then the question is, how many mistakes would you make, given that one of the experts is kind of infallible, but we don't know who that expert is? If you use follow the leader, you would end up making D mistakes because until the last day, you wouldn't have zeroed in on the best expert, right? So even in this case, follow the leader will can potentially have number of mistakes to be like D minus 1. Okay. So it's not FLL, this is FTL. So FTL achieves regret, which is basically D minus 1. Now, in the worst case, the regret can be D minus 1. You were wrong for D minus 1 rounds. On the D today, of course, there's only one expert left who must be the infallible, right? But can you do better? Is this D factor really the best you can? I say you think of D as being very, very big. It's not like humans predicting. It's really, you can just imagine bots or models, and then you're trying to just make inference based on these predictions. Okay. So what might be a better strategy? Again, think intuitively. Yeah. But what are you following? Like you're predicting based on the average majority, right? Exactly. So in the general case, when there are 0, there can be numbers, you can say average. Right now it's just 0 or 1. So let's just say I'm going to do follow the majority. Which again makes sense. Instead of following the best expert, just look at what all of the experts are predicting, and I'm just going to follow the majority vote so far, right? So we keep a set of infallible experts, and we predict set of eligible experts, not infallible, sorry. If you knew that, that would be fine. Eligible experts, and we predict according to the majority. Okay, so more formally, the algorithm would be, I'm going to start with all of the possible experts as eligible. And an expert will consistently be eligible unless they make a mistake, right? In our present scenario, once you make a mistake, we know that person is not the best expert. So we'll throw that person away. Okay. So on each day, we predict according to the majority of experts in A of t minus 1. And throw away all experts who made a mistake. Okay, kind of a brutal strategy where one mistake means you're out of the game. Okay. And the cool thing is that this can actually do much, much better than follow the leader. It's in fact going to do exponentially better. Okay. So a simple theorem that we can show is that if there exists an infallible expert, the regret of follow the majority algorithm is at most log base 2 of the total number of experts. So if you have 1,000 experts, it's going to be log base 2 of 1,000, which is basically like 9 or 10. Okay. And why do you think this is true? I mean, we'll prove it formally in a second, but there's really just like a one sentence sort of explanation. Why?
Just each time we have an expert.
Exactly. Right. So every time we make a mistake, we make significant progress in narrowing down the set of experts, right? We made a mistake means a majority of the eligible experts made a mistake. So we made a mistake, okay, that was costly, but we learned a lot from it. We threw out half the experts who are currently eligible, at least half. And of course, the infallible one will always be there. So you will never throw out that person. So the number of mistakes must be bounded. Okay. So the punchline is just that each time we make a mistake, we throw out at least a half. Okay. But potentially you might need log d rounds, okay, but never more. But nevertheless, this is kind of simple analysis to describe. But let me do a more cumbersome analysis because we will extend it later on, right? So I'm just going to do the same calculation, but in a slightly more seemingly tedious way by defining a potential function. Okay. Because this will be useful later when we develop an algorithm which can work in a more general setting where we don't have infallible. That's too strong an assumption. So at every time t, I'm going to define a potential function to track how well the system as a whole is doing. Okay, meaning all of the experts combined together, right? So this is just the number of experts still under consideration at after day t. Okay, so in other words, this is just the size of A of t, the set of eligible experts that we were defining. Okay. So the analysis, whatever we said that, we never throw out an expert, and every time you make a mistake, you throw away at least throw out the infallible expert, but every time you make a mistake, you drop at least half. Let me just write it in this language. So the first property we know about this is that phi of 0 is D. Every expert is initially eligible. 2, if we make a mistake, on day t, okay, because we are going to throw away at least half of them, the number left will be at most half of the previous one. All right. So now we can, do the same thing. So L of t, remember, is the number of mistakes our algorithm, which in this case is FTM, makes, by day t, right? So we can clearly say that this is at most right. So every time we make a mistake, we hit the previous size by a half factor at least. So in the end, the total number of experts left is at most 1/2 raised to the power total loss. Okay, the same argument, I'm just trying and writing it in a very painfully laborious way. Okay. And lastly, we have the following simple claim that at any time there's one expert who is alive, because there is an infallible expert who never made a mistake, so that person will never be thrown out. Okay, so this is for all. So if we combine these two things, we get 1 is less than or equal to 1/2. Okay, and just sort of a paragraph long explanation of this one line thing saying that every time you make a mistake, you throw away half. But we'll see that the same template we can use for the much more refined algorithm. We'll define a potential, track how it changes when we make a mistake, and then show a lower bound based on the performance of the best expert, combine the two, and we'll get a bound on the total loss. Okay, so that's the reason for doing it in this way. Okay, so far so good. And but there is like issue, which is the assumption of infallibility is very strong. Okay, so somehow saying that once you make a mistake, you get thrown out is very harsh, right? It makes sense if you imagine there is a best expert who will never make a mistake, but that's again a very high bar. So what if I tell you there are experts who are, maybe make 10 mistakes or something? You can still try and do something. But in general, our goal is to not assume anything about the performance of the expert. I just want to match whatever the best expert is going to do. I don't want to assume that, oh, they have a very good expert, I don't have a very good expert, or anything like that. Okay. So how can I sort of, is there a natural way to extend this algorithm to this more general setup. I don't have infallibility, but I still want to kind of match the performance of the best expert. So what would be like a natural thing to try? Any suggestions, guesses? Like, imagine what you would do, right? So, I have some predictors who keep saying, okay, something is going to happen. And if a person is consistently wrong, what would you do? Right? So you just have to quantify this. Like, how is less and more going to be defined? Okay. And this is something that shows up really in betting markets, and that's where kind of in portfolio management and so on. As I said, this idea was discovered there as well, right? So, like on betting horses or anything like that, right? So imagine you assign some sort of confidence factors to each expert, okay? Or in our case, we'll just call it weights to the experts. Okay, so we're going to assign some weights to the experts. And so the weights are meant to say that, high weight means this expert is, we have higher confidence in this expert. If the weight is 0, that means we basically throw away that expert. Okay? And how should you predict now? What's a natural extension of the follow the majority strategy? Follow the weighted majority, right? So you have some sort of like, okay, this expert I have a confidence of 0.1, this expert 0.9, this expert 1. So I just take the weighted majority of these things. If there are 1,000 experts, each with confidence 0.1 saying the opposite of one expert, even if the person has high weight, maybe I should go with 1,000 experts with low weight because there's so many things. Okay? So predict according to the weighted majority. Okay, so this is how we are going to make the prediction. So once you make the prediction, you know the truth and you get some information about the experts. So what should you do after this? So if any algorithm in learning with experts has 2 phases. One, how you aggregate the predictions of the experts into your own prediction. And the second part is to update your sort of confidences about the experts, right? So at the end of each day, we had to go back and sort of revise our, evaluations of these experts, okay? So the intuitive thing is that mistaken experts, we have to decrease weights. Okay, so if an expert made a mistake on that day, I want to decrease their weight. You can also just consider the flip side where if an expert is correct, you increase their weight, but just stick to one. Doing both is unnecessary. Okay, it's equivalent. So whenever an expert makes a mistake, we decrease their weight by something. How much we decrease depends on the actual algorithm, right? So in some sense, they follow the majority algorithm is similar, right? So you just say whenever they make a mistake, we're decreasing their weight to 0. We're just throwing them away. From now on, they're not under consideration, but that's very harsh, right? So what else can we do? We don't want to be so harsh that once you make a mistake, you'll get 0 weight going forward. We want to kind of find something which is smoother, right? And the natural thing that actually works is, so what can you try when you make a mistake? How should I update the weight? Any guesses? Again, think simple. Half it, yeah, makes sense. decrease weight by half. You can even make this half a, sort of a constant that you can tweak. Maybe every time they make a mistake, I say, okay, your weight decreases a factor of 0.9. Okay. All right. And this is exactly the follow the weighted majority algorithm. So we start with every expert getting weight 1. All right. So we have weights for each expert that change over the time. Right? So WT comma I is the weight of expert I at the end of day T. Okay. All right. And then for T equals 1 through however long you run the game, we make a prediction based on weighted majority. Okay. So that's the prediction phase. And then there is the update phase where we go to each expert and say, for each expert, if EI made a mistake, you set WT comma I is WT minus 1 comma I. Right? Okay. And otherwise, the weight does not change. Right? So you just keep the weight as it is. Else, okay. Any questions? A natural enough extension of follow the weighted majority. And just to kind of expand on this prediction based on weighted majority, it just means that you add up sum of weights of experts predicting up is greater than or equal to sum of weights of experts. Okay, so predict according to weighted majority just means look at all the experts' predictions. Add up the weights of those who predicted up. If that is more than those who predicted down, just go with up. Otherwise, you say down. Okay? All right. And follow the weighted majority actually does quite well. So we will show shortly that the loss of follow the weighted majority, loss of follow the weighted majority is at most okay. So it's very close to, the guarantee that follow the majority had for the toy case of infallible expert. So if there is an infallible expert, loss of the best expert is 0. So I'm saying this is going to give me something like 2.4 times log D base 2. But more generally, no matter who the best expert is, I'm potentially slightly off, but not by more than like this 2.4 factor. Okay. It's some progress. It's still not ideal because what I would really like is the gap between my loss and the loss of the true expert to be very small. Right now, this is saying I'm off from a multiplicative factor, but that doesn't mean the gap is small. Okay, does it make sense? This is still some progress. We got from nothing to slightly worse, or in a factor 2 worse than the best expert. Okay, up to this additive log loss by a simple algorithm. Okay. All right. So how do you prove such thing? The template, we'll see it 3 times, so that's why I did it this way, is the following. We're going to define some potential function, show that it starts out with some value. Whenever we make a mistake, the potential function decreases a lot, but there is a lower bound on the potential function. So these 3 steps. Okay, but what should the potential function be? Any guesses? What would be the natural thing to track about the performance of the system so far? You can think of it as some kind of evaluation of how well all of the experts are doing together. Okay. So what would be a good way to define the potential function? If you take a guess, and we'll see if it's correct or wrong, or if you can make it work. Yeah. Yeah, exactly. That's very natural, right? And somehow, if everyone has very low weight, that means that everyone is doing badly. Okay, so it's as I said, you can think of it as some kind of quantification of how well the experts are all doing together. Okay, so phi of t is just going to be sum of all of the weights of the experts after day. Okay, so sum of all the weights, right? So that means phi of 0 is actually d, because every expert started out with a weight of 1. Right? And then we will show the sort of claims as before. The first claim is to say that if we make a mistake, on day t, then the potential decreases significantly. In the infallible case, the size decreased by a factor of half. Here it's slightly, it's not as harsh, but it still decreases by a factor of 3/4. Okay, and the 3/4 comes in because if you made a mistake, that means that a weighted majority of the experts made mistake, and all of their weights got hit by a factor of half. Right? So half of the total weight was wrong, and half of that, you decrease all of that by half, so you basically decrease by a factor of 1/4. Okay, which is how 3/4 comes in. All right. Okay, but let me just do this proof. Right. So So we can think of it as 2 sets. One is all of the experts who were actually correct, and all of the experts who were wrong. Right? So for each of them, the experts who are correct, their weights haven't changed. Okay, the expert did not make a mistake, the weight doesn't change. The expert made a mistake, their weight gets halved, right? But so I can write this as half of I'm just splitting this into half and half so that the accounting becomes easier. And this is just sum of all the weights of the experts, right? So I just get phi of t minus 1 times a half here, okay? And because of the fact that we made a prediction, that means that the experts who were correct, they were the minority. The total weight was less than the weight of the correct experts, of the incorrect experts, right? So that means this whole thing is at most by 2. As follow the weighted majority was wrong. Okay. And this is just 3/4 of phi of t minus 1. All right. Okay. So every time we make a mistake, it becomes 3/4. So if we just repeat it, we get a simple claim that phi of t is at most 3/4 raised to the power whatever loss that we have times d. Okay, every time we make a mistake, we hit with 3/4. So overall, it's 3/4 to the number of mistakes times. Okay. And lastly, we need some kind of lower bound control that the system, as I said, potential is some kind of quantitative measurement of the entire system of experts quality, right? And the nice thing is we can actually show a lower bound. That look at the best expert. Every time they made a mistake, we hit their weight with a factor of half. The best expert only made certain number of mistakes, then their weight isn't too small. Okay. So here L star of t is loss of the best expert. Right? So if this is the person's loss, then W of best x of t comma best expert is exactly this much. Right? So if I made 10 mistakes, my weight would be 1/2 raised to the power 10. If I made 100 mistakes, it's 1/2 raised to the power. Okay. So that's it. One expert at least has this much weight, and phi of t is sum of all the weights is at least lower bounded by this. Okay. And now we can put these two things together. Implies okay, and you have to take logarithms or whatever, implies 4/3 to the power L of t is at most okay. So let me take log base 2 of this inequality, and I get this log of 4/3 base 2, and that's where the 2.4 comes in. Okay. So this implies that the total loss that I have is at most this factor. And this is 2.4 or roughly 2.4. Okay. All right. So all of this is very good. Now let's talk about regret of t so far, or follow the weighted majority. Remember, regret is our loss minus the best loss, which in this case is going to say is at most 1.4 times L star of t plus log d base 2. Okay, so I'm subtracting L star, so it's 1.4 plus 2, right? And as I said, this is pretty good, but not like exceptionally good, because we really want to close the additive gap to the best x. Okay. And in fact, there is this very important notion of no regret algorithms. Kind of a misnomer. No regret doesn't mean the regret is zero, but asymptotically the rate of the regret goes to zero, right? So what does it mean? It's okay for me to have some loss, but as I play the game more and more, I want my gap to shrink, which is not necessarily happening here. So if I play the game 100 times, you got some loss on average. But if I play the game 1,000 times, I should get a much lower gap on average, because I had more time to kind of learn who the best expert would be, right? So what we would really like to have is the average regret over the time, meaning this ratio to go to zero, right? So such algorithms are called no regret algorithms. Okay, as t goes to infinity. So imagine, even the best expert is wrong 10% of the time. It's not unreasonable. Even if the best expert is also wrong 10% of the time, that means L star is like 0.1 times t, right? So in that case, my regret is not going to zero. It's always fixed. No matter if I play 1,000 times, 1,000,000 times, on average, I'm still incurring a non-trivial loss from the expert. Okay? So no regret would be very good, because it's saying that as time goes on, I am actually converging to the best expert's performance in the limit. Okay? Any questions about this? So that's kind of, in some sense, no regret is like the holy grail. Can also be more quantitative here, but getting no regret is the first sort of most significant bit. Okay? All right. And one thing that we haven't explored so far is our algorithms are deterministic, meaning give me the expert predictions. What I'm going to do next is fixed. Right? There's no randomness. I'm not tossing any coin. It's completely predictable what I'm going to say based on what the experts are going to say. Right? And unfortunately, there's this thing which says that there is no regret deterministic algorithm. Okay. So in particular, you can't go back to this and say, oh, maybe I shouldn't be updating it, penalizing wrong experts by a factor of half. What if I'm more sort of lenient, I'd say 0.9, or what if I'm more harsh, I hit them with a factor of 0.1. None of those are going to give you a no regret algorithm. Okay, so this requires a proof, but let's just take it for now. And in fact, you can show that any deterministic algorithm cannot do better than 2 times L star. It cannot do better than a factor of 2. Like, follow the weighted majority got 2.4, but it cannot be better than a multiplicative factor. All right? Okay. So is this the end of the story? Thankfully, no. There is a very important randomized algorithm which actually gives you a no regret algorithm. Okay, so concretely, there is a very simple, it's almost like they follow the weighted majority, but with a small twist. So it's called the multiplicative weight method, or MWM. It's going to be a randomized algorithm. And what we can show for this randomized algorithm is that the expected loss that our algorithm is going to incur is at most L star of t plus something. So there's no factor of 2 or anything like that here. It's actually an additive gap. The loss that we incur is going to be at most this much. Whatever the loss of the best expert is, plus something additive. How much additive? Square root of the time. Okay, so if I ran it for 1,000,000 steps, then my additive loss from the best expert is going to be at most square root of 1,000,000 times log of the number of experts. Okay. So in particular, the expected regret of multiplicative weights is at most 2 times square root t log. So this gets the holy grail that we wanted. The average regret over time is going to 0 as the time goes on. Okay. Does it make sense? So we are getting an algorithm which, as time goes on, will converge more and more towards the performance of the best expert. All right. So it's an additive gap, not a multiplicative thing. So if the best expert had a performance of 0.1, we will actually be 0.1 asymptotically. All right. So any questions about the statement? And why no regret is kind of very nice, because you're getting this additive gap and this ratio is going to 0 over time. Okay. All right. So let me finish by describing the algorithm, and the next lecture we'll analyze it and potentially see some applications. But it's as I said, kind of a simple algorithm. But it takes a mouthful to write, so I'm drawing this big box. There are various variants of it, but all of them are kind of equivalent. I'm just writing one here, which is most consistent with what we just discussed. And it's helpful for analysis, but you can also do many, many other things. Okay. So as before, we start with some weights, which are 1 for each expert. Okay. And in some sense, the only thing that changes is how we make the prediction. Updating the weights is still going to be the same. Whenever an expert makes a mistake, we are going to hit them with a factor in the weight. Okay, but we're going to be more lenient. Instead of half, we're going to maybe do 0.9. Okay, it's going to be some tunable parameter. So on day t equals 1 through t, we have to decide how we are going to make a prediction. And this is where the difference from follow the weighted majority comes in. So there we aggregated all of the predictions and said, okay, look at the weights of all of the experts. If the weighted majority said up, go up. If the weighted majority said down, go down, right? So what we're going to do instead is not follow the weighted majority, but think of the weights as our confidence in the experts, okay? And we're going to pick an expert at random based on our confidence. Okay, that's the only change. So we pick an expert I at random with probability proportional to WT minus 1. Okay. Whatever their current weight is, we're picking them with probability proportional to it. If expert 10 is 1,000, whose weight is 1,000 times more than expert 1, the chance that expert 10 is going to be picked is 1,000 times more than expert 1. Okay. More formally, probability EI is picked is exactly the weight of that expert divided by the total weights, just to make it like a probability distribution. Okay, so we first pick an expert at random this way, and then we just follow this expert. We're not going to aggregate the votes anymore. We're going to pick an expert at random based on the weights, and then I'm only going to follow this expert. Okay, so this is the prediction part of the algorithm. Okay. And as I said, the updating part is exactly the same with a small change. So we update the weights by saying if expert I made a mistake, then some factor eta, which is once again called the learning rate for a good reason. If they don't make a mistake, the weight does not change. Okay. This is called multiplicative weights, but because we're keeping track of the weights and we're multiplying the weights by a factor every time they make a mistake. Okay, so this eta is something that we have to choose, and we will choose it appropriately. Okay, any questions about the algorithm? All right. And we'll show basically that this algorithm gets okay, this is the guarantee that we're going to show. So whenever I run multiplicative weights with learning rate parameter eta, I get a loss which is very close to the L star. As the learning rate decreases, my multiplicative factor decreases, but the additive factor increases, ln d by it. And if you balance these two, you get the square root t term. Okay? All right. So when we come back next lecture, we'll prove it. The proof is exactly the same thing that we've already seen 2 times. You define the potential, which is a measurement of how well the entire system is doing, add up all the weights. And then we'll track how the weights change when we make a mistake and how the weights change in terms of like, best expert. Okay. So we'll talk about this in the next lecture and, see some other applications. All right. I'll see you all on Monday.